Okay, so today we're going to talk about a very important concept in quantum computing or quantum information, that's entanglement. And there are many different approaches to. One second, let me just check my mic. Okay, yeah, so there are many different approaches to kind of introduce this concept, but I want to start with probably a direction that we kind of have discussed in one of the classes, is that when we write down, okay, when we say that why do we need to go to quantum computing, right? At the time we say that, okay, for n qubit, which are all binary, right? You can be in ground state or excited state or in a superposition. For n qubit in quantum mechanics, you have 2 to the nth, okay? You will be in superposition of 2 to the n states. Okay, this is kind of clear, is because your state can be in, for example, okay, alpha 1, 0, 0, or n qubit at 0 state, and then alpha 2, 0, 0, only one qubit on, excited state, and then keep going, right? So eventually you will have, 2n state. Okay, and then a quantum state can be in superposition of all these states. And at that time, we also say that, I'm not sure if you guys have given a little bit thought in this, is that we kind of correct one concept, is that the right way to write down a quantum state is to write it down in all these 2 to the nth, okay, possible eigenstate, and then write down the coefficient in front of it, and then this is a superposition of all these 2 to the nth state. There's a different way, okay, at the time we say that you can write it down, but then it's wrong, right? It's that you write down the state of individual qubit, and then you just write them together, right? This is more like a classical way, right? If you put n qubit or n bit together, you describe individually, okay, this bit is in this state, that bit is in that state, and then it looks very natural. It looks, you would think, okay, intuitively we think this is correct. But at the time we say, okay, this is not correct, it's because a very simple argument here you can see is that for this state, for this type of measurement, this type of expression, okay, there's only 2 times n coefficient. Right? Each state you only have 2 possible coefficients to describe this superposition. So for n qubit, you only have 2 to the nth coefficient to describe this state. Okay, compare with the complete superposition of the n qubit state, you actually need 2 to the nth coefficient to describe the quantum state. So what this means is that although, okay, this looks intuitive from a classical point of view, but then it's not a complete description. There's a lot of missing information, right? If you create a quantum state, there's a very large probability that cannot be written down as this state, right? Because you have 2 to the nth coefficient while here you only have 2 times n coefficients. So a lot of the information is missed, right? So the definition of entanglement is closely related to this. Is that let me write down the entanglement definition. Okay, for a state with n particles, okay, for a state with n particles, it doesn't have to be binary, right? Because you can be atom, you can be molecules, you can have a lot of states. Okay, if your state cannot be written down as a direct product okay, if your state cannot be written down as a direct product of individual particle states, okay, this is for particle 1, okay, all the way this is particle n. If your state cannot be written down as direct product of all these individual particle states, that means your state is entanglement. Okay, and another way you can think about it is that as long as individual particle state, okay, individual information of individual particles cannot express your state, that means your state is in entanglement. Okay, and I can give you guys probably 2 very simple examples, okay, about which is entanglement, which is not entanglement. In general, okay, if you just write down, well, this is a little bit deeper other than the definition. In general, if 2 particles have no connection at all, okay, physically have no connection. For example, I brought an electron here, and then I pick up an electron from somewhere else. And these 2 electrons are not interacting with each other. Okay, they're just sitting there by themselves, and there's nothing happening. In this case, you don't have any entanglement at all. The reason is okay, they 2 are separated. They're individual particles. For example, if your state is that you have electron 1, electron 2, okay, they're all in this atom 1, atom 2, they're all in this superposition state. Okay, and then if you do a direct product, you can see that their state is okay. You can use this definition to check that this is not entanglement, because this can be written down as a direct product of 2 particles. And another example is okay, this state. Right? If you look at this state, and then you pay close attention, you can see that, okay, particle 1 is always in the excited state. Right? 1 here, 1 here. And then the one that really in superposition is the second particle. Right? So this one actually can be written down as 1 cross product. Okay? So as long as you can write it down as direct product, then it is not an entanglement. Okay, and if you can prove that, it cannot be written down as direct product, then it is entanglement. So example for entanglement, very simple example for entanglement. Let's see. This is so-called EPR state or Bell state. Later I will explain what it is. right? This state. And then I think we've discussed this in previous class, is that if you try to write this down, okay, if you try to write this down as direct product okay, if you try to write this down as direct product, what you will find is that you actually can't find a set of alpha beta, okay, to satisfy the coefficient, right? And I think at the time I think we kind of explained it is that because 0, 1, okay, there's no 0, 1 state, so alpha 1 times beta 2 is 0. There's no 1, 0 state, so beta 1 times alpha 2 is also 0. Okay, so eventually we see that, okay, if one of these have to be 0, then the coefficient in front of 0, 0 and 1, 1 also has to be 0. So there's actually no way, okay, to decompose that into this. Okay, and this is entanglement state. Okay, this is entanglement state. And it's very interesting. One thing that, okay, this type of state was first actually discovered by Albert Einstein. Okay, that's why it's called EPR state. E is the initial for Einstein. PR is the initial for the other two co-authors on that paper. So what's special about this state, okay, if you look at it, is that, let's say if I want to measure atom 1, right? By looking at it, you will see, okay, there are 50% chance atom 1 is at 0, 50% chance atom 1 would be 1, right? So it's 50-50 for 0 and 1. And if you measure atom 2, it's actually the same, right? If you first measure atom 2, you also see, okay, 50% chance is 0, 50% chance of 1, right? So it looks like when you do measurement, it's the same as this state, right? Because this state, atom 1 is in superposition of 0 and 1 when you measure it, so 50% 0, 50% 1. Here is also 50% 0, 50% 1 for atom 2, right? But then the critical difference is here. The critical difference is when you measure atom 1, okay, and in quantum mechanics, the postulate, we know that if your result is 0, your state will collapse into that state, into that eigenstate, right? If your result is eigenenergy is corresponding to the ground state eigenenergy, your first particle, okay, will collapse into 0 state. So this state will be gone. Okay. So after the first measurement, let's say if your result is 0 for atom 1, then your state will become 0, 0 state. Okay. So what that means is that if you measure atom 2, okay, after measuring atom 1, you are no longer 50-50 now, because you only have a 0 state here, right? So now, if you measure atom 1 first and then you measure atom 2, okay, your atom 2 result will be always the same as the atom 1 result. Okay, this is kind of clear in the state description, right? There's no state that's 0, 1 and 1, 0, right? So when you measure it, they have to be the same. Okay. So a quick observation here is that what it tells us is that if you measure individual particles, okay, let me put it in a different way, okay. So from here, okay, we say that if you know, even if you know all the individual coefficient of a particle, it doesn't necessarily mean that you have the entire knowledge of the complete state. This is also the same case, okay, if you just measure individual particles, it doesn't mean that you can get the entire information of the state. Right? After the measurement, you kind of have to compare the measurement result many, many times, and you can eliminate some of the other state. So what it says is that in quantum information, okay, if you really want to get this exponential, 2 to the nth coefficient, or 2 to the nth called Hilbert space size, you have to have entanglement. Is because some of the information is actually stored in the correlation between qubits. Okay, there's a global information stored between them, right? For example, this state, what this state really tells us is that particle 1 and particle 2 are in a quantum correlation, right? If particle 1 gets 0, particle 2 will also be 0. If particle 1 is 1, particle 2 will be also 1. Okay, so this is a quantum correlation, and the information is in this correlation. Okay, it's in this correlation. Okay, so I hope here, okay, by showing this coefficient difference and by showing you, okay, the measurement between two separate particles and then the entanglement state, you can kind of get the idea that if you want to have this exponential speed up in your quantum computing, you have to have entanglement state. Okay, so entanglement is actually one of the critical ingredients in quantum computing. Now, I want to go a little bit deeper into the concept of entanglement, and then specifically explain why Albert Einstein will pay attention to this little state, right? It's just right, because it's just a very kind of funny state, and then why Albert Einstein would like to discuss about it. And Albert Einstein actually published very few papers. He only published important results, and by today's standard, he won't get tenured at UVA. But also he doesn't apply for funding. Okay, so definitely he's not going to get tenure in UVA, which is in some way really a shame. Well, I'm not criticizing UVA. He won't get tenure in most of the universities today. Okay, so sometimes we have to reflect, okay, what we are really doing in the university and whether it's correct or not. So so why Albert Einstein proposed this EPR state is that he actually tried to find a loophole in quantum mechanics, right? Because he's not a big fan of this probability interpretation, right? Well, there's a famous argument between Albert Einstein and Niels Bohr, right? Albert Einstein says that the God won't roll the dice, okay, and then Niels Bohr replies that you don't know what God wants to do, right? So, which is kind of all valid, okay. And then a lot of physicists at that time actually, deep down they agree with Albert Einstein, right? Because this probability thing is kind of annoying. But then what they also observe is that numerous experiments agree with the probability interpretation, and actually this argument goes down and down and down, and then eventually for this, the paradox in this state eventually was resolved in the 1980s by experiment. So the thought experiment by Albert Einstein proposed in 1935, the year 1935, is that the paradox he proposed is that suppose, okay, you have two particles, and then they have some kind of interaction, right? And then after the interaction, you release them, and then one goes this side, the other goes that side, right? And by this, he claimed that, okay, you can create some entanglement state because of conservation laws, right? For example, if the momentum, okay, net momentum is 0, and then you kind of control the electron, and the electron, for example, electron 1 can only go, okay, minus x direction, or minus x direction or minus 1 direction, right? If this is state 0 to state 1. And then because of momentum conservation, you know that if electron 1 goes this side, electron 2 has to go that side, right? If electron 1 goes down, then electron 2 has to goes up, right? So this create an entanglement state. At that time, it's quite new. Okay, nobody really pay attention to this. Okay, but notice that here, okay, for electron 1 going left is 0. For electron 2 going right is 0. Okay, and so this is a thought experiment. At that time, people don't have the way to actually create this. Okay, so the argument is that, well, the left and right is relatively kind of, let me put it this way, it's a little bit too conceptual. Let's assign a better way, okay, to understand this, or to explain this. Okay, let's say the electron, okay, after the electron, what is conserved is the color. Okay, and then we're going back to the black and white thing. Okay, the color of the electron, the net color is gray, right? And then, sorry, the color is conserved in a way that, okay, for if the first electron is black, then the second electron will also be black. And then if the first electron is white, then the second electron is also white. Okay, it's the same thing as 0011. We just use a different notation. Okay, black and white. Now, imagine this thought experiment. Okay, so I came from China. Okay, so there are 2 electrons, and then I really want to send my mom Thanksgiving. Well, Thanksgiving is not celebrated in China. Let's say I want to send my mom a New Year's gift. So I keep one of these electrons. So one of the electrons is kept by me, electron 1. After this state is generated, so electron 1, okay, kept by me is UVA. And then I ship the second electron to my mom in East Coast, China. Okay, I know if you know the city Guangzhou, okay, the third largest city in China, actually has 3 times the population as Virginia in the city. Okay, so that's a place where I grew up, and yeah, it took me quite a while to get used to the Virginia style. Okay, and okay, so one of the electrons at my place, and the other electron is at Guangzhou in China. Okay, and these 2 places are around like 10,000 miles away from each other. Okay, so 10K mile away from each other, and then also if you want to fly from here to there, if there's a direct fly, let's say you can you can rent a private jet. That would be a 13-hour flight. Okay, so that's how far away they are. So the question that posed by Albert Einstein is that, okay, suppose I do a measurement here at UVA, okay, and let's say the result is black, right? There are 50-50 chance. Let's say the result is black. Now the question is, when will the electron kept by my mom turn black? When would that happen? Does it happen instantaneously? Or does that happen after the distance divided by the speed of light, right? Suppose there's something transmitted, right? If you think about it, okay, how does the electron at my mom's place know that my electron turns black? Right? Simply, how can it know that? Right? And this is a question that Albert Einstein posed, is that he actually point out, at that time what he wants to do is that he wants to point out a contradiction between special relativity, which means nothing can travel faster than the speed of light, right? And then the assumption that quantum mechanics is complete, right? So he proposed like this: if my mom and me, okay, we measure this at the same time. Let's say we have a clock that are completely synchronized, measure at the same time. And when my mom measured it, the electron should not know the state of my electron, right? Because they're so far away, and then it actually took, if you calculate it, it actually took 0.03 seconds, okay, for the speed of for the light to travel from one place to another, and also they're so far away, so it's actually difficult to point, okay, the light directly at me. So Albert Einstein argued that, okay, if my mom measured the electron, okay, very shortly after my measurement, right, very shortly after my measurement, for example, 0.01 second after my measurement, then there should be no information flow able to reach from my electron to my mom's electron, right? Because the speed of light is, the limit of how fast information and energy can flow. So then Albert Einstein argued that, okay, then what should really happen is that when you do this measurement, your mom will also get 50-50, black and white, because when it measured it, it seems that not knowing my result, right? And then when I measured it, it's also 50-50. Right, so in this way, you would be able to, if you measure this long enough, you would be able to create a state or create a measurement result that is black-white or white-black, okay, which are not in your original state. Right? So this is the argument posed by Albert Einstein, saying that, well, your quantum mechanics is simply, well, there's a loophole, right? It's not complete. Any questions here?
Can particles even stay in an entangled state? Have you thought that through?
Yeah, that's a great question. In theory, well, right now we know that. At that time, people don't know. Right now we know that, yes, they will. And there's actually an experiment that done by Jianwei Pan, the scientists in China, that they use those quantum satellites, okay, to distribute a pair of entangled photons, okay, send it from satellite and then reach it to two different telescopes, on the ground, and then those two telescopes do the measurement, okay, on the photon, okay, black and white, or whatever the photon state they use, and then they actually verify that those two photons are entangled, right? So what that means, let me think about what's the distance between those two telescopes. I think at least they did it in the east side of China and then west side of China, so that's about 5,000 kilometers apart from each other. And then I know that they plan to do it with Austria. Okay, then that would be beyond 10,000 kilometers. So at that time people don't know, but right now we know. Okay, they can stay entanglement when you're very far apart from each other. And now let's think about it. Okay, now let's think about it. Is that let's ignore the fact that information travel, the travel of information actually need time, right? The speed of light or whatever carrier you use. Let's ignore that. Let's just think about whether it's possible for an electron to send information and then to be received by the other electron, right? Regardless of how long it would take. And I don't know if you guys have ever made international phone call, okay? And how that works is that the phone, okay, send out, well, I think you guys must be familiar with this, is that the power, okay, if you have a light bulb or if you have a RF source, and suppose it's not directional, then the power at a distance r away from you should be, the total power divided by r squared, right? It's radiating like a sphere, right? And then the further you go, right, the energy density reduce r squared. And then, so that if you think, okay, so that the fact is that sending information that very far away from each other is actually very, very difficult. And then it's for example, nowadays, you pick up your phone and then you make a call. What really happened is that your phone, okay, send a signal to the nearest tower, right, by radio frequency or microwave frequency. And then that tower send it to a more powerful tower, and then eventually send to a center that convert that electrical frequency, okay, to a fiber, right? And that fiber travel, okay, to the data hub. I think here is either Richmond or Washington, D.C., and then that fiber goes underwater, okay, across the, well, this side is hard if it's in Los Angeles and go all the way down to the east coast of China. But this side, okay, you have to go to West Europe, and then, from there, West Europe, and then you go through another very, very long fiber and all the way to China, and then again converted to radio frequency and tower, and then sent to your cell phone, okay, and that's the amount of trouble, okay, or that, let me put it in a different way. It took 5,000 years of civilization, okay, to kind of figure out a way for us to do it. It's very difficult to imagine that electron, the simplest structure not the simplest, one of the simplest structure in the universe, somehow can point his information, right, towards a certain direction, and then send information out, okay, whether I'm black or white, and then received by another electron sitting there. Okay, if that's true, then I don't know whether we should have electrical engineering major, right? We should just ask electron, how can you do that, right? And then worship electron instead of developing devices. So the idea that electron and electron can communicate long distance is just nonsense, right? It's just not practical, and it would be just wrong. Okay, so so how is this resolved, right? How is this resolved? At the time that people are actually not able to do this experiment, and then the first experiment, I think, was done either in 1970s or 1980s by a French scientist. Okay, what he does is that he generated a pair of entangled photon. Okay, and then I'm not sure which property he used on the photon, but you can think of either polarization, okay, is conserved, or angular momentum is conserved, or one of those. Okay, so one photon goes to the left, another photon goes to the right, and then you let it travel a very long distance, and then here you arrive at the measurement. Okay, this side there's also another measurement. Okay, you let this distance to be long enough. Okay, and then you do this measurement, and you can kind of see that, okay, the design, you want this latency to be as small as possible. You want this, well, let me rephrase it. You want this photon to roughly arrive at the same time, right? So that you eliminate the chance that when the photon is being detected, he can communicate with another photon, right? You want to eliminate this possibility. And why people cannot do this experiment in the past? Okay, there are several reasons. First is that before it's actually to generate entangled photon, you actually need nonlinear optics, and nonlinear optics is only possible if you have laser. And laser was invented, I think, in the 1960s. Right, so and then nonlinear optics was discovered 1 year after that, and it actually took about 20 years of development, also material development and a lot of technique development, to actually enable people to do this entanglement photon pair generation. Nowadays, it become kind of relatively simple. Is that, for example, it took my group about a year, okay, to redo this, so that we are able to use a lot of the prior knowledge established by other people. Okay, so other than that, another difficulty you can see here is that the speed of this measurement here. Okay, when the photon arrive at here, all the measurement actually took a little bit of time, right? For example, you arrive at time t1, but then the measurement is not instantaneous, right? Just like if you want to see something or if you want to take a picture, there's actually a readout time and there's actually exposure time, right? When you took an image on your camera. So there's actually need to be you have to add a delta t, which is the readout time or the measurement time, okay? Now on this side, when you arrived, okay, you arrive at time t2, and then again you have a measurement time delta t, right? So the idea is that your delta t, okay, if you want to control this experiment really well, and you want to make sure that this measurement is unaware of the result generated from the first measurement, then what you want is that you want to have T1 almost equal than T2, right? So they're doing this measurement at the same time. And also you want delta T to be much, much smaller than L divided by C, right? It's because like if you have a measurement readout time, then you're not very sure, okay, exactly at what moment you finish your measurement, right? And if your measurement takes a long time, then you can argue that, okay, maybe in the middle of your measurement, the photon send information to another photon, and then they actually are able to communicate with each other, right? So this is actually very important. And I want to tell you guys that, okay, for L equal to 300 meters, a very, very long distance, usually lab space are like tens of meters, delta T would be 1 microsecond, right? 1 microsecond corresponds to 1 megahertz. Okay, 1 megahertz. And you can probably ask your parents, okay, what type of computer they use in the 1990s or 1980s. Okay, the clock speed is actually very close to this. Okay, so being able to do very fast measurement is also a recent achievement in the past 40 years or 50 years with the development of electronics. Okay, so this experiment, okay, actually have to wait, from 1935 until the time that until 1970s or 1980s to be done, and then the measurement result clearly show Albert Einstein is wrong and then quantum mechanics is correct, right? So the measurement result is that although, okay, these two are measured independently at the same time, and then the distance is very much farther than the delay time or measurement delay time in your measurement system, you will always see black, black, or white, white. Okay, that's the only two possible result. Okay, even if the measurement is done at the same time, there's no chance for these two photons to communicate with each other. You still get black, black, white, and white. Okay, and this is interesting, right? Then so the question is, okay, what went wrong? Okay, how does the electron, how does the photon, okay, the second photon, how does it know what result come from here? Does it mean that the photon not only able to send out information, but then the information is faster than the speed of light? Right, that's really, really, that's in some way you can call it revolutionary, but the other way it's just so wrong. Okay, the reason of this, I'm not sure if you guys know why nothing can go beyond the speed of light. The argument is actually come from special relativity. Is the causality argument? Is that when you go something travel, okay, faster than the speed of light, and then in the Lorentzian transform, which is the one of the major results from special relativity, what you will see is that there will be a negative sign on your time, right? So it's that the time actually travel backwards. So the problem with that is that now you can do time travel, and then that can violate causality, right? It's like if I somehow travel back in time and then I mess up the first day of my mom and dad, and then there will be no me, okay? So, okay, then if there's no me, how can I go the time travel and then mess up the first date, right? So it's like there's, just causality is something that intuitively you would kind of have to believe. Okay, whether that's really the case or not, again, has to be tested by experiment. Right now, since we're not able to get anything, well, we're not able to get any close to speed of light, so I would say, okay, just trust the causality, since you have no way to do time travel, right? So, yeah. Okay, so the argument is from causality, and if you look at the causality argument, then you see that there's actually a loophole here. Is that it doesn't say, okay, it's not like nothing can travel faster than speed of light. What it's really saying is that information and energy cannot travel faster than speed of light, because information and energy is the thing that can mess up the causality. Right? If I send some information to my dad saying that, oh, maybe you shouldn't date this woman, okay, that can change things. If I send some energy, okay, let's say I build a wall between my mom and dad, okay, they couldn't meet, that would change the result, right? So the causality argument, the requirement is only that energy and information cannot go beyond the speed of light, okay? So in the EPR measurement, let's look at it again. So if you have that causality argument in your mind, then let's think about it. Is there information travel from me to my mom, right? If we do this measurement at the same time, you would say, yeah, there is information, right? Because if I get black, my mom also get black. If I measure white, my mom also measure white. So it seems that there's information flow. Okay, from me to my mom, or from my mom to me. But the fact is that this is not information flow. This is just correlation. Right? Think about this. Let's think about it. What does it mean by sending information from me to my mom? Okay, if I really want to send information, I have to be specific whether I want to send black or white. Right? I have to send either black or white. Unfortunately, when I do this measurement on this state, I have no control. It's 50% black, 50% white. Right? 50% black, 50% white. So there's actually no way for me to actually send any useful information from me to my mom. Okay? And you say, okay, but what about the fact that after you measure it, your mom also measured black? Does that count as information? No. Because even before the measurement, as long as we know that we're preparing this state, we know 100%, okay, as long as the experiment is perfect, when I measure black, my mom will also measure black. It's not additional information. We did not generate any additional information. Okay, this is just information we already know when we prepare this experiment, right? So this entire experiment, what it really is a quantum correlation. Okay, a quantum correlation. And then there's no information flow, so actually there's no need to even discuss causality. Okay, and this measurement, okay, there are many different variations, and then people actually found loopholes in this measurement, and then try to fill the loophole and loophole, and then well, I didn't follow the state of art, but from what I know, that all measurements are proving that quantum mechanics, it is what it is. Okay, you measure black, it's black. Okay, both of them are black, both of them are white. There's no case that you can violate that. And yep. Okay, and now. What can we learn from this? Okay, what's the takeaway from this? Is that, a very good takeaway is that I think for a lot of you, okay, especially you guys are still very young, is actually to ask good questions. Okay, just ask good questions. Sometimes a good question is more valuable than a good answer, especially in some areas, for example, mathematics. In mathematics, people actually really like those researchers and mathematicians that ask a lot of good questions, so that everybody has something to work on. Okay, And then if you're the type of people who solve problems very quickly, people actually hate you, right? Because you hit all those problems, and then so all other people lose their jobs. And so Albert Einstein, okay, this EPR paradox, he actually doesn't think about like entanglement. He doesn't think about like how entanglement can be used for quantum computing. None of those. Okay, it's not coming from a practical point of view. It's simply from a curiosity-driven, or say just try to appreciate try to question the completeness of quantum mechanics. And then he discovered something else that later, okay, this has become one of the most important things in today's quantum computing, and also quantum information. Next, this Thursday, we can quickly talk about how to use entanglement to play the devil's game, and then you can actually win the game with 100%, 100% probability. Okay, thank you guys.